Okay, so we're going to talk about the dissociation of weak acids and bases now. In a previous conversation, we said that strong acids and bases only go one way, right? So if this were a strong acid, what is this? Formic acid? If this were a strong acid, it would dissociate, like would donate an H plus to H2O, right? And it would go all the way, 100% all the way. That's what we said in a previous conversation. That's if it were strong. But now it's not strong, it's weak, because that's what we're talking about. We're talking about weak acids and bases, and they go both ways, right? In other words, when this system is at equilibrium, it turns out there's a sizable population both of this and of this, right? They both exist in solution at the endpoint. All right, so our learning goal for this is for this section, is to write the expression which tells us how much it goes in one direction. How much, and we're going to do that by writing an expression for the dissociation of a weak acid or weak base. All right, so because the dissociation of strong acids and water is essentially complete, the reaction is not considered to be an equilibrium process. It is not equilibrium. However, weak acids partially dissociate in water, only partially, and therefore when they reach equilibrium, there are some molecules which are yet undissociated. Formic acid, which is the picture we saw on the previous page, is a weak acid that dissociates in water to form the hydronium ion and form 8. All right? The question is, how much formate is there? How much? If it went all the way, we would say it's strong. If there was 100% and 0% of this at the end, we would say it was strong. But it's not strong, it's weak, so that means there's something less than 100%, right? Well, as with other, we're going to figure out how to express how much there is. There's no way you can tell by looking at how much there would be. You have to be told by measurements, okay? So, as with other dissociation expressions, the molecular concentration of the product is divided by the products is divided by molecular concentration of the reactants. This is not going to mean a whole lot to you because we haven't done other dissociation expressions, okay? So let's just say that the molar concentration of the products is divided by the molar concentration of the reactants, okay? So in other words, we take the products, which, I mean, products, which are hydronium and formate, and we put them up here, the concentration's up here, right? And we take the reactants and we put it down here. Now, water is a reactant. However, since water is a pure liquid with a constant concentration, it's omitted. In other words, we don't put the H2O down here. You get that? We don't put the concentration of H2O here. And the way that you know that is because it says pure liquid, right? So you'll get used to this, but for now, let me just tell you, we do not put the concentration of water down there, all right? Now, sorry for the background noise, but I'm just going to keep recording here. There is, it turns out that this dissociation constant tells us the extent to which the reaction goes forward. Why? Well, this tells us the ratio of the products to the reactants. That's what this is. It's a ratio, right? And so since this ratio is very small, can you see 10 to the minus 4? That means it's very small. That means we don't have much products. That means this acid mostly doesn't go that way. It mostly goes that way, right? The denominator is much bigger than the numerator, okay? So when the value of Ka is small, the equilibrium lies to the left. That is, it favors the reactants, which is what I said in a previous slide. When it's large, that means the equilibrium lies to the right, and it favors the products, okay? Weak acids have small Ka values, while strong acids have very large Ka values. We actually consider them to be infinity. All right? We do the same thing for bases. If we have a base, then some reaction here, I've got methylamine here. If I take methylamine, it's a base. That means it's going to produce hydroxide ions in solution, right? And we can also have a K for this, right? Where it's the products. Oops, I did that. There's my reds. Let me get rid of this. Oops. Okay. Let's go here to yellows. My methylamine you see the concentration of methylamine is on the bottom, right? So it's the products over the reactants again. All right, and this is also a small K, which means that we mostly have much more reactants than we do products. All right, so here are some weak acid bases. Table 11.4 gives some Ka and Kb values. They tell you the stronger that they are. The bigger they are, the more products they have, because remember the products on the top. So phosphoric acid has a Ka of 10 to the minus 3. That means it's a stronger acid than acetic acid, which has a Ka of 10 to the minus 5. Does that make sense? Because the products are on the top, we have, how do you spell products? With a P-O? No, P-R-O. It's the concentration of products over the concentration of the reactants, right? That's what K is. K is equal to that. And so the more products we have, the bigger the number is, right? And so there's the biggest number on this table is this number, 7.5 times 10 negative 3. Okay, so that's the strongest acid. And the weakest acid is, wow, very weak. Look at this. Hydrogen phosphate, which is 2.2 times 10 to the negative 13. So basically, yeah, pretty small. Okay? And we have some bases down here too. Methylamine has a pKa of 4.4 times 10 negative 4. Ammonia has a pKa. I said pKa. Sorry, Kb of 1.8 times 10 negative 5. Right, and so that means that methylamine is a stronger base than ammonia. All right. So strength with table 11.5, I'm going to leave for your reading. Okay, it's just a review of the things I've said just now. I do want to go to a learning check, and then we'll cut this off. Write the acid dissociation constant for nitrous acid. So if you get a question like this, actually, let me encourage you to pause the video now, go back and look at the notes that you have for the previous part of the lecture, and make a guess. You'll learn this way better if you guess first. Okay, so I'm going to pretend that you paused it. Maybe you did. Hopefully you did. And I'm going to say, all right, in order to write the acid dissociation constant, first of all, I've got to write the reaction. It's HNO2. It's an acid, so it's going to react with water. Okay? And it's going to go both ways because it's weak, because it's not one of the 7 strong acids that we memorized. And so it's going to go to H3O plus nitrite. Okay? And so the dissociation constant expression is going to be Ka is equal to the products of the reactants, right? Which is equal to H3O plus. Sorry for the background noise. We've got a lot of friendly people in the house right now, and we're chatting it up. And I don't want to delay this lecture any longer, so I'm just recording over top of it. All right, and that's the acid dissociation expression for nitrous acid. We will practice this more, but hopefully that makes sense. All right, talk to you soon.